Hello, this is Mahandadidia. This module is incorporated in the book on liquid formulation. The book categorizes liquid formulations as solution, suspension, and emulsions. The scientific discipline employed in integrated approach to development of innovative product is the main focus of this book. This approach is used by innovative pharmaceutical, cosmetics, and biotechnology institutions from selection of excipients to formulation development to commercial scale manufacturing, and it is captured in the book. The subject matter is based on sequences for each category of liquid formulations, and these are physico-chemical characterization, pre-formulation, composition and formulation, lab scale and commercial scale processes, quality by design, and formulations used in clinical studies. The modular approach is used in the book so that reader can access each module independently for their own learning and references. In this module, we'll cover formulations of emulsion. We'll build on physico-chemical characterization of emulsion presented in earlier modules. We'll begin with characterization of formulation and composition, which are the building block of product development. We'll cover this topic in 5 submodules. The theme of first submodule is characteristics of conventional dispersed phase, continuous phase, and emulsifier for both water and oil and water emulsions. In separate submodule, we'll focus on auxiliary ingredients that are used in emulsion, deep dive into formulation and lab processes for both, again, oil and water and oil emulsions. We'll cover separately double emulsions composed of water and oil. And finally, we'll look at siloxane-based emulsions with emphasis on double emulsion. So, first thing we want to look at is dispersed phase, continuous phase, and emulsifiers in this submodule. Other things will be covered separately in different submodules. Target product profile. This is used both in pharmaceutical and cosmetic development. We start with product use and label claim. Then we define what kind of emulsions we want to develop. Oil and water and oil, or double emulsions. We want to also state what is our rheological characteristics. That's extremely important in cosmetic as well as pharmaceutical products. We look at stability and then specific use and dose of administration, oral, IV, skin, hair, face, etc. We also incorporate in target product profile laboratory and commercial processing, including equipment and packaging and storage conditions. Composition characterization is very critical. Emulsion is a biphasic liquid composed of immiscible liquids which are stabilized by the use of emulsifier. The dispersed phase, as shown in blue here, and the composition characterization is represented in the diagram on my right. You see a dispersed phase or a globule phase, in this case oil, and blue representing water or the aqueous phase. The surfactant and co-surfactant, i.e. emulsifiers and co-emulsifiers, need to cover the entire globule phase. And we use mixtures of them. And in this submodules, we will look at this in more detail. Let's compare oil and water and oil emulsion. What are the similarities and what are the differences? We start with the dispersed phase. Obviously, in oil and water, it's composed of oils. In water and oil, it's an aqueous or water phase. Other way around for continuous phase, in oil and water, it's water, whereas water in oil, it's oil phase. The most important difference is emulsifiers and co-surfactant. The HLB, hydrophilic lyophilic balance, needs to be greater than 10 for oil and water, i.e., emulsifier will be water loving. It's other way around for water and oil emulsions, where emulsions are oil loving. Rheology can be adjusted, electrolytes can be added to both water and oil and water emulsions. Spreadability is good, water and oil and water. Spreadability is good in oil and water, and it's very good in water and oil because oil is outside. However, it may feel oily if the formulation is not carefully formulated. Uses are different and they can be interchangeable. So key component is emulsifier that needs to have a sufficient effect on interface to make a stable emulsion. And selection of emulsifier and co-emulsifier blend is based on what's called HLB bridging. And we will look at that in detail in this submodule, which says that HLB of the emulsifier and that HLB required by the oil needs to be similar. Let's look at each of these characteristics in a little bit more detail. Dispersed phase or a globule. Oil and water, oil is globule. Water and oil, water is a globule. So drugs and active needs to be soluble in oil and has to have high partition coefficient so that they do not leach out of the oil phase. Dispersed phase, they need to form a single phase in both cases. In one case, is oil and miscible excipients. In other case, is miscible and soluble excipients. HLB, oil and water globule. Emulsifier and the required HLB needs to be greater than 10 and needs to be similar. In water and oil, emulsifier and required HLB needs to be similar and less than 10. We'll look at electrolytes and preservatives in more detail in separate submodules. Continuous phase. Oil and water is water, whereas in water and oil, it's oil. Again, excipients needs to be miscible or soluble in each of these phases respectively. Rheology is extremely important, and different type of materials are used to adjust viscosity of oil and water and oil. Electrolytes, preservatives, and pH and buffers are generally incorporated in oil and water, water being outside, and generally not used or not as important in water and oil. Though they can be incorporated, they are not very critical. Colors, sweeteners, flavors, and suspenoids are generally used with caveat that sweeteners may not be required in water and oil emulsions. Emulsifiers. This is extremely important. Griffin in 1949 presented HLB classification, and he provided an empirical unit from 0 to 20 and said less than 10 were emulsifying agents used for water and oil, and greater than 10 or greater than 8 can be used for oil and water emulsifying. And he provided calculations. And this is still used in determining calculated HLBs for surfactants. Most commonly used is HLB relationship between saponification value and acidity value of the fatty acid component. Example shown here for polysorbate 20, HLB is calculated to be 16.7. Let's look at this video in a little bit more detail. So when we mix oil and water, we have enormous amount of choices in oil as well as surfactants or emulsifiers. As I said, it was developed by Griffin, and it's provided that HLB less than 10 are generally preferred for water and oil emulsions, and higher than generally 10, but as low as 7 can be used for oil and water emulsions. And there are HLBs greater than 30 now. And one can calculate the proportion of oil required HLB and corresponding surfactant HLB. And we will do that in this module. This is done by a bridging technique. And generally we use more than one emulsifier and co-emulsifier. That gives us better coverage and better interface processes. So emulsifier and co-emulsifier blends are based on HLB bridging. So interface, again, let's look at it. If I were to use only single emulsifier shown in red, it will not provide the full coverage and would leave lots of openings. And these openings will make emulsifier use not very productive in the sense that emulsion will be commercial. The interface becomes very important. And if I were to use only the red surfactant or emulsifier, it will not provide sufficient coverage on the globule, which will result into emulsion instability. When we use co-surfactants shown in blue, it provides better coverage and allows emulsion to be kinetically stabilized. So in order to do that, we need to make sure that the emulsifier's HLB, which is calculated, needs to be comparable to the required HLB of oil. And that will allow emulsifier to provide sufficient effect on the interface. So let's focus on what is required HLB by an oil or oil mixtures. Required HLB is experimentally determined by making blends using emulsifiers with high and low HLB. These blends are then used to make series of emulsions with oils. And then HLB itself, the required HLB for the oil, is then based on emulsion characteristics, interfacial tension, droplet size, zeta potential. Does it separate on centrifugation and stability of it? In the appendix at the end of this submodule, we have provided several oils and required HLB values of those. These are also available in numerous literature, and most of the suppliers will provide the required HLB of oils. We will look at composition of emulsifier and co-emulsifier blend and how do you calculate that. This will be for parenteral cisplatin, oral, and water emulsion, and we'll figure that out based on HLB bridging. Cisplatin is a chemotherapeutic drug used in several cancer type diseases to treat them, and it's very effective. One of the composition contains cisplatin at 0.05%, has 3 different oils, soybean, cottonseed, and peanut oil, has 2 surfactants or emulsifiers, X-phosphatide and pluronic, and has a water aqueous system composing of glycerin, chelating agent, pH adjustment, and vehicle itself. The required HLB from the literature for soybean oil, cottonseed oil, and peanut oils are known. They are respectively 10, 6, and 6. HLB for peanut oil and egg phosphatide are calculated and are also known, and they are 10 and 6 respectively. So this is the information we have. What we want to know is how much emulsifier I need to add and how much co-emulsifier I need to add so that the HLB of the emulsifier mix is going to be very similar to the required HLB of the oil mix. So the first step in bridging is determine the required HLB of the oil phase. And this is proportional, and required HLB of the oil phase is the sum of each oil's contribution to that HLB. So each oil is going to contribute a portion of its HLB based on its concentration. And in the following, this is shown. So required HLB of a particular oil plus HLB of that oil times concentration of oil divided by the concentration of total oil phase. This gives us a proportional value of the HLB. Oh boy, there is a mistake in this. Oh, there's a mistake on the slide. The required HLB of the oil is equal to HLB of the oil times concentration of the oil divided by the concentrated total phase. So it gives us a proportion. So for soybean oil, proportionately, 10 is the HLB, and it's 0.8%, or 80%, or 810. So the contribution of soybean oil is 8. Similarly, contribution of cottonseed oil is 0.9, and contribution from peanut oil is 0.45. So total HLB required is equal to 8 plus 0.9 plus 0.45, that's 9.35. So required HLB for oil and water emulsion by these three oil mix is 9.35. Once we have that information, we can now calculate the concentration of each of the emulsifier and co-emulsifier. So again, we use bridging method and to calculate concentration. Again, it's proportional. And I've used only 2 emulsifiers as given in the example to simplify the explanation. Concentration of egg phosphatide is given by the equation below. It's total concentration of emulsifier used in the formulation multiplied by required HLB of oil minus the HLB of chloranic divided by the difference between the two HLBs. And similarly for chloranic. And we can calculate now the concentration of each emulsifier. Egg phosphatide HLB is given by putting values in the equation. We get the concentration of the emulsifier, in this case 1.0005%. For chloranic, we substitute values in the equation above, and we get 0.195 as the concentration required for the emulsion. So the composition then is given in this slide. The oils 8%, 1.5%, and 0.5%. The required HLB for that oil to make a stable emulsion is 9.35. The emulsifier and co-emulsifier at concentration of 1.005 and 0.195 respectively provide the same HLB. This gives us a starting composition of the product. By no means HLBs are perfect, but this provides us a starting point for formulation. Based on that, we can build our formulation development and plan and optimize formulas. Appendix, as I told you, provide HLB of selected oils for both oil and water and oil. And I will leave reader to read that on their own. Additional appendix for HLB of selected oils for oil and water. Again, they range from 15 for stearic acid to very low, about 6 or 7 for different oils. Emulsifier HLB, there's an enormous literature on it. The values can range from low as 1 for glycerol distearate to very high for sodium lauryl sulfate of 40 and potassium oleate for 20. So again, there are thousands of emulsifiers used in cosmetic industry as well as some in pharmaceutical, and ranges of HLP from 1 to as high as 40 are available.